Welcome back. In this lecture, we're going to talk about the sine function. Now, in trigonometry, we have various trigonometric functions, like sine and cosine. You may have heard of these, but we're going to talk a little bit about what these functions do. Now, you can think of the sine function as a black box. If we draw a box, then we can input a value into the box and get a value back out of it. Now, we can treat sine like a black box. Let's say that we pass in a value to sine, like sine of t, for example. And if we pass in some value t, the sine function is going to return a value, and we can call that value sine of t. So what exactly does the sine function do with our value t to give us some different value? Well, we can define the sine function in terms of right triangles as follows. If we have a right triangle, then one of the angles of a right triangle, by definition, is a right angle. That's going to be this angle here. Now, we can define the side of the triangle that's opposite the right triangle as the hypotenuse. So we call this side of the triangle the hypotenuse. And we typically pick one of the angles of the triangle to analyze, such as this angle here. Now, we can call this angle theta, the Greek symbol, which is kind of a mathematical tradition. Now, the sine function takes an angle as input. So if we pass theta into the sine function, then we get something out of it, right? And this angle exists on a right triangle. Now, if we call the side opposite the angle theta opposite, and we call the side adjacent to the angle adjacent, then the sine function is defined as the opposite divided by the hypotenuse. In other words, it's this ratio here. And the cosine function is defined similarly. We pass the angle theta into the cosine function, and the cosine function returns the adjacent side divided by the hypotenuse. So adjacent over the hypotenuse. So these are the trigonometric relationships on a right triangle to the sine and cosine functions. So as we can see, the trigonometric functions are closely related to right triangles. Now I'm going to bring your attention over here to this circle. Now this is a unit circle. A unit circle has a radius of 1 unit, which means it has a diameter of 2. Now the circumference of a circle is defined as 2 times pi times the radius of a circle. But in our case, we have a circle with a radius of 1, and 2 times pi times 1 is just 2 pi. So for our unit circle, we have a circumference of 2 pi. Now let's imagine that we can start on the x-axis at the point 1, 0. So right here, we're at the point 1, 0, right? And if we start walking along the perimeter of the circle, we can form a line from the center of the circle outwards to the point that we've traveled to. So if we've traveled this far on the circle, we can form a line from the center of the circle outward. And we know that wherever we are on the perimeter, this line will always have a length of 1. Well, wherever we travel on the circle, we're forming a right triangle. And here is the triangle we're forming. And we're also forming an angle with the x-axis. So right here is our angle, and we can call this theta. So we can use the trigonometric functions to calculate the lengths of these two sides on the triangle in relation to theta. We know that the sine of theta is equal to the opposite side of the triangle divided by the hypotenuse. But in our case, the hypotenuse is 1 because this is a unit circle. So this length of the triangle is 1. In other words, we have a right triangle, we have an angle theta, and we know that sine of theta is really just the opposite over 1. So sine is the opposite side of this triangle. But the opposite side of this triangle is actually our y-coordinate. So we can say that y equals sine of theta, on the unit circle, of course. Now, the cosine is defined as the adjacent. So this is the adjacent side. The adjacent side divided by the hypotenuse, but our hypotenuse is 1. So we can say that cosine of theta is equal to the adjacent side divided by 1, or just the adjacent side. And this is actually our x-coordinate here in xy space. So we can say that x is equal to the sine of theta. So now we have trigonometric functions on the unit circle defining our x and y coordinates. So this is very useful. Now, we've mentioned that theta is an angle, and it looks like right here theta is approximately 45 degrees. And if we're halfway between this point and the topmost point on the circle, this is indeed 45 degrees. But we also know that the circumference of our unit circle is 2 pi, and if we travel all the way around back to the starting point, we've traveled by 2 pi units, and we've rotated by 360 degrees. So we now have a new unit of angular measurement, and this unit of angular measurement is called radians. We know that 360 degrees corresponds to a distance traveled around the unit circle of 2 pi. And this is how radians are defined. So 360 degrees is equal to 2 pi radians. And we could simplify this by saying that half of 360, or 180, is equal to pi radians. So the distance we travel on the unit circle is our angular measurement in radians. So if we travel half of the unit circle, we've traveled 180 degrees, or pi radians. So if we rotate by pi radians, we've rotated by 180 degrees. And if we rotate by 90 degrees, we've rotated by pi divided by 2. So this is pi halves. And 45 degrees is pi divided by 4. So that's how we can convert from radians into degrees. Now the reason I bring this up is because the sine and cosine functions are often defined in terms of radians rather than degrees. Now, the interesting thing about the circular nature of the trigonometric functions is that they create periodicity. They create sinusoidal motion. By sinusoidal, I mean going back and forth. Let's see what I mean by mapping out the sine function as a function of a value t on a linear graph here. Now we know that if t starts off at 0, then our sine value is going to be our y value. And our y value at t equals 0 is simply 0. And as we increase our angle here on the unit circle, we see that our y value is increasing all the way up to a maximum of 1 at pi halves. So let's say that this point here is pi halves. Then that means we're going to smoothly increase up to 1 on this graph. So the graph looks like this. That's what our curve for the sine function looks like. And once we reach pi halves and we continue going along the unit circle, our angle is increasing all the way to 180 degrees. So let's say that this point here is pi. Then we know that our y value, which is the sine, is decreasing all the way down to 0. So we're coming all the way back down to 0, and we hit 0 right at pi. And then as we increase, we get to this point right here. Well, if this is pi halves and this is 2 pi halves, or pi, then this is 3 pi halves. So we'll say that this point right here on our graph is 3 pi halves. And our y value is decreasing all the way down to 0, reaching 0 at pi, and then it continues to decrease. Our y value continues decreasing down to a minimum of -1 at 3 pi halves. So at 3 pi halves, we will reach -1 in the y, which means our curve will smoothly go all the way down to -1. At which point, as we continue increasing, as our angle increases, we're going to get all the way back to 2 pi, which is 360 degrees around the circle. And by that point, our y value has gone all the way back up to 0. So now our curve goes smoothly back up to 0, at which point we repeat the process. That's why we say that sinusoidal functions are periodic, because as our value increases past 2 pi, this is 2 pi here, we're going to go all the way back up to 1, all the way down to 0, and continuing down to -1, all the way back up to 0. So our function is going to continue oscillating like this, going up and down and up and down in a smooth manner. And the cosine function behaves similarly. Let's take a look at what happens on this graph when we graph the cosine function. So the sine function is in red, and the cosine function of t is going to be blue, okay? So as t starts off at 0, we know that cosine is our x value. It looks like I wrote sine, but this should actually be cosine here. X is the cosine, which is the adjacent, this side here, the x-axis value. So our cosine is our x. So if we start off here, we're starting off with an x value of 1. So the cosine function starts right here at 1. And as we increase, as we walk along the perimeter of the unit circle and we reach a value of pi halves, then our x value decreases down to 0. So at pi halves, we decrease down to 0 here. So here is our curve for cosine. It looks like this. Now as t increases, we're going to get all the way to pi, and our value for x is going to continue decreasing, going into the negative direction until we reach -1. So at the value of pi, the cosine goes all the way down to -1 in a smooth manner. And as t continues to increase, our x value is going to go back up to 0 by the time we hit 3 pi halves. So cosine goes back up to 0 here. And as we continue along our way, we'll eventually make it to 2 pi, at which point the x is going to increase back to 1 again. So at 2 pi, we're going to increase in a smooth manner back up to 1. Now notice something interesting. These two curves look an awful lot like each other, and the truth is they are the same curve. The only difference is the sine function is shifted over just a bit, and it's shifted over exactly by pi halves. So this is what the sine and cosine functions do, and we can use them in game development very often whenever we want periodic behavior like this. Say we keep a running time from the start of the game moving onwards, and every frame we're adding delta time to it. Well, that's why I call this variable t, because if this graph represents some value with respect to time, say an object's z location, then the z location of an object is going to sink and rise and sink and rise. And then you have this bobbing behavior. We call this sinusoidal behavior. Sinusoidal because it looks like the sine function. Doesn't that make sense? Okay, so this is a very beautiful thing, and we're going to make use of it in Unreal Engine when we apply the sine function to the elevation of our item and give it sinusoidal behavior. I'll see you soon.